Hello and welcome to SDL development. This is going to be for network server programming. My name is Nate Nestler and this is for Hyperactive Studios. Okay, so we've been talking about other areas of SDL. Now we're going to get into coding out the server in Linux here with SDL, and it'll also work in Windows too. I'll prove that both ways. But getting started here. Let's look at what we need to do. Now our code hasn't changed. Well, okay, I've kind of gotten a clean slate for this particular one because we're doing the server. So the server doesn't need a cube or OpenGL or anything of the sort. When we're doing, let's explain a few things here first off. When we're doing this, we need a couple of things happening. And I'm taking this from the standpoint of client server. And there's multiple setups that you can have. But the best way to do this is to actually go about it in a logical fashion. So basically what's going on is we're going to have the server here, and then we're going to have a client. Let me draw it for you. Sure. Right. So say we have like the server here. That is probably quite literally the most ugly circle ever. Oh, I don't care. Okay, so let me just scale this up. That's the server. Alright, and then these smaller ones are going to be clients. Alright, and then say we got clients connecting to our server elsewhere. And that's cool. Nothing wrong with that, of course. And they're connected like so to the server. And so this is how we're communicating back and forth between them. And I'm definitely taking it from the standpoint of client server and not peer-to-peer network, because a peer-to-peer network, although cool, is very limited, and I can show you real quick why that is a problem. Okay, so this is a client server here set up. Now if I was doing peer-to-peer, and you can see how this works. So if I want this little guy here to communicate with this little guy over here, then he sends a message to the server, and the server sends a message to the other little guy over here. And then this way two clients can communicate with it. And you can see that we can pretty effectively communicate between all the different machines. The one downside to this is that we have to have one machine act as a communication point for all the other machines, which are clients. So that main communication point is going to be called the server. So this is what's going to basically determine how we send messages to the other computers, right? And then the other computers are called clients, and they're the ones that connect to our server, and they're the ones that send the message to the server in order for the server to send to the other clients or handle some action or something of that nature. And the reason why we want to do this, if we didn't do this, let me show you what you'd have to do instead. Alright, so say I wanted that client to connect to that computer, cool, and that's how that computer connected with that client. And then this client would have to connect with that one, and this one would have to connect with this one, and this one would have to be connected with that one, and then this one would have to be connected with that one. So on and so forth for every client. Just to help make that hit home a little bit more, let's have a look at doing one more like this. So let's say I did this one over here too, okay? So this one would have to connect to that one, and that one. You start to see the spaghetti here. The number of connections that are required and handled is becoming insane quickly. So you see, this becomes unmanageable very quickly of what's happening here. So that's really nasty. You know, you can go on and so forth, and this is just going to become a massive color mess real quick here as we connect each computer with each computer across the whole network. And that's going to be your peer-to-peer system, you know, where two computers connect with each other and there's no server. Well, as you can see, the number of connections go up exponentially for the number of computers added, because for every computers added you have to do, you know, like that many more connections for that number of computers on the network, you know, each time. So, you know, say I want, you know, another connection, you know, say we had 5 connections, we had probably about like 25 connections going back and forth. We had one more, we have like 36 connections. I mean, it'd be that ridiculous. Somewhere in there. It's probably a roundabout number, but you get the idea, basically. With the server, look how many connections we have to have. 1, 2, 3, 4, 5. And then 6 for the sixth one. That's it for the whole network. Now, otherwise, we're talking like 36 connections for our clients if we're doing peer-to-peer. So doing server-client makes a whole lot of sense. So because of that, I've taken it from the standpoint of doing just server-client. So that way we don't have this big connection mess, and that it makes it more efficient for the network interactions. And so now we only have 6 connections instead of like 36. So because of that, we will save a tremendous amount of time. Now, the downside, of course, is that you'll have to have one computer be the server. But this is how most modern games and, well, just about any applications are done for server connections. And this is a star configuration. So we're doing the server at the center, and we're having all the clients connect to it. And then this way, it also makes it very useful too, right, and easy. Because say we just want a client to drop off the network, that's fine. They just disconnect from the server, and then they're gone. You know what I mean? And then the rest of the network continues to work. So you don't have one computer that's, it's not going to take down the network if this computer, shuts down. That certainly saves a lot of problem. And this allows clients to connect and leave a game while it's running easily. You know what I mean? In and out, or any other type of server application that you're doing. It could be a message server or anything of that nature, a chat server, anything like that. So it certainly simplifies the process and makes it a lot easier. Now, if I'm doing the only thing where we have a downside to this, of course, is if the server goes down, then everyone is disconnected from the game. So, of course, if the server ever goes down, the game is no more. But otherwise, this makes it life simple. Our server is also going to be our host, because our server is going to hold the data for the game, more or less, on it. And that way it makes it easy for it to correspond with the other clients here. So the server is going to know what's going on overall, and it's just going to correspond this data to each of the clients as needed. So that's essentially how it works, and that's what we're talking about. So this is client, and this is server. So we're going to do the server first, because this is going to be the main connection hub. And I already showed it working earlier in a previous video. So let's have a look at what's going on. So if def here, space underscore C++, so same setup as before, pound include std, std lib here, and then else include stdlib.h, so that whole setup there, end if pound, and then we have the if def here, apple here, so if it's going to be apple, we're going to do it this way. Now you're going to notice we're going to do a standard SDL, but you're going to notice something new and different here, and that is that we have our SDL underscore net.h. Now I'm going to show in a later video here how to actually set this up for Windows, because it's actually more difficult to set this up for Windows than it is on Linux, but we'll get it set up, and it's not brain surgery or anything like that. It's not real difficult. It's just more tedious and I guess more time consuming to hand install each of these files. But we're just going to do it on Linux here first, and then we'll have a look at running this and making this work on Windows next. Typically too though, I have to say you do typically want to run your server on Linux, because its internet connections are about twice that of another major operating system that's made in Redmond, Washington State. So, and it also has 50% speed increase in saving to hard drive. And that's on average, not an absolute for this particular application or that versus that application. I'm just saying on average. And so you'll see a much lower usage of memory and hardware and things of this nature. And Linux is also a free operating system, so you can throw it on many servers as you want. And if you wanted to, you could set up something on like Amazon Cloud, for instance, Elastic Cloud, and run your server up there and be able to handle lots of clients on a single game. So you can do fairly large games and very cost effectively too. I would definitely lean towards one of their high compute type servers for handling with large memory. That'd be probably more what you're wanting to do, and not like a large data type server, because that's going to match more of what you're doing as far as if you're doing a game type server. So you're not going to be storing data during a session so much as you are going to be processing data as fast as you can and offloading it to others. So that's going to be the idea here. Okay. So you'll need lots of RAM and processing power basically for these types of servers. Okay? And Linux is going to work very good. Not to mention you also see a massive speed in core usage too. Linux tends to get a 90% utilization of each core, whereas another major operating system only gets about 33% or somewhere in there, if I remember right. I'm trying to go off memory here. Yeah, it's significantly more effective if you're dealing with Unix and Linux for processing power, network utilization, and also speed at which you save and access hard drives. So Linux is extremely tight and streamlined on the core of the operating system, so it goes very fast. So typically, even if you are running your client machines, if you're running your games on, say, Windows or something like that, on client side, you probably do want to run your server Linux, as you'll probably get a better performance versus some other operating systems out there. Okay, so with that, pound include here, we have our so we're including our SDLnet, and same thing here. So we got our, for Linux, we've got this included. We also need to include a list. Now we're going to use a list and not a vector. And the reason why we're going to use a list and not a vector is the way it lays out in memory. So let's look at that real quick here for how it lays out in memory. So I'm just going to create a new one real quick. I don't really care, just as long as it gives me another one too. Okay, that works. Alright, so let's look at a vector versus a list, okay, in C++. So as a vector lays out in memory, it goes like, okay, so say this is our memory here, and we got different we got different memory locations here for each part. I'm just going to haphazardly draw these, I don't care. Wow, that's ugly. I'm drawing this with the mouse. Oh well, you get the idea. Alrighty, so say I'm in here, and this is the difference between a vector and a list. So a vector is going to just put the data into each part here, each piece. And so it's using what's called a linked list, where it's able to find the next location in memory without having to necessarily have them together. So like it literally links this one to this one, and this one points to this one, and this one points to that one, and then that one points to that one, and that one points to that one, and that one points to that one. Okay, and so on and so forth. And so in this way, we know where the next point in memory is. So this becomes really simple, right? What if I just want to remove this one data here, element, from the memory? No problem. We simply just point to the next location here. See? And now we've eliminated this one in the middle here, which is cool. And this one no longer exists. So that's great. That lets us delete things very quickly and easily from our list here without much headache or much work. And it takes very little processing power just to update that pointer to the next location. Bam, done. It's now gone from the list. Now what if I want to add something back in? Well, it's not a problem. If I add to the list, it'll get added to the end, right? So I knew I shouldn't have drawn something at the very end. Ah, I thought I should reset to blue. Mistake. Alright, so say we have this right here. Say we want to add another one into there. Okay, no problem. So we add some data in here, and we need to now add that to our list. Well, it's not going to be a problem because now we're just going to set this being the end. We're going to now point to that memory location for the next element. And so now we just added one. Very simple. We just put the data in there and we point to where the data is in our list structure, and bam, we've added one in memory. So you can see it takes very little processing power in order to add and remove. It's just nothing more than updating a single number that's a memory address. And remember, a memory address is just like, say, a person's house. You know, how to, like the address to someone's house, so that way you can find their house. Same thing goes for these memory addresses. Okay, now let's look at what happens with a vector instead. Now, a vector works in a different way. And I'm not going to draw this as much because doing this is going to take more time for a vector than it did for the list. Okay. Alright, so we're just going to lay it out like that real quick, okay? Okie dokie. Now I'm going to create another layer real quick here, just because I'm going to be, yeah, thanks. I'm going to be switching this on and off, so I don't want to deal with this a whole lot. Okay. So say I've got some stuff here in memory, right? And this is, you notice how this is laid out in memory, right? So this is going to be slow when we go to read it back, right? So when we go to read this list back, we have to sit there and read these different memory locations and skip over other ones and then find the ones that we're looking for as the computer scans through the memory to find the data. And it's told where to go to it, so it knows where to jump to it, but it still has to, takes time for it to skip over this other memory to get to this next location. So, okay, so say we got a list, something like this, right? Okay, great. Now, the thing about this is, and here's our data, not in the list, I'm sorry, our vector. This is our vector and this is our list. Sorry, real quick, let's just do, I don't care what color it is. Okay, so let's say list over here. Did it go? Okay, goodness gracious. What on earth? Alright. Alright, there we go. So be it. So this is going to be our list. And this is going to be our vector. Wow, this is really hard to write with the mouse. Alright, our vector. And that couldn't possibly be any uglier than what it is. Alright, but anyways, so be it, right? Okay. So say I want to delete this particular element here in memory. Yeah, I'll do this one because I don't want to do as much headaches. Alright, so cool. No problem. Just remove this one in memory, right? But with a vector, we're not going to simply just be able to remove it and have the next one point to the next one. It doesn't work that way. They're consecutive memory locations. So what we have to do instead is then move this one to this one, and this one to this one, and this one to this one. So the way we do that, of course, is by now drawing in one here as we move this one out, right? So that one is now gone. Now we need to move this one into that location instead. Alright. So we now move that one to that location. Okay, and now we need to move this one to that location there. And then remove it. Okay. And so you can see it starts eating up a lot of work in order to just move and update that memory location. But obviously the vector is faster for reading back data in memory. So there's going to be times where vectors are going to be better, and there's going to be times where lists are going to be better. And it's really up to you what kind of algorithm you're using or what you're doing is going to make more sense or not. consecutively laid out memory, if you're just constantly hitting a set of values and they're not changing very much, you're better off with a vector. If you're constantly updating and changing values, then you're much better off with a list. So depending on what you're doing, it depends on what your setup's going to be for this. So because we're going to be adding clients in and out of our system here, as they can just drop off and come back whenever, maybe faulty connection, maybe they connect lots of times back and forth. Because they're going to be changing on a regular basis, we're better off with a list. So I chose a list. Whereas on a joystick, the chances of someone adding and removing joysticks on a regular basis is going to be relatively slim. Most people are just going to leave their joystick plugged in, or they'll only plug in one or maybe two joysticks. You're not going to have 32 joysticks plugged into a computer, right? But you could have 32 clients dropping on and off on a server. So in order to keep the speed up, we're going to use a list in order to make things faster. So that's why we need to do #include list. Alright, so with that, we're going to do struct here, and we're going to call it client type, and we're going to set up our client as you expect. Open curly brace to start our struct here, and then we're going to do a TCP socket. Okay, so what is a socket? A socket is a connection, if you will. So every time we have a connection with our little server here, right? So this would be a connection on the client side. Let's go ahead and draw this in here. So that has a connection, and then our server has a connection to that one, right? So they each have sockets, right, that they're communicating with. And these sockets have ports, so we know what number that for which socket to connect to, or which port to connect to, if you will, for each place. So you notice that the server has to have a lot more sockets than the clients. Clients are relatively simple compared to the server. They're only have one socket to deal with, and they only have to do communications between the server and themselves. Basically just with the server. So that makes life easier. Whereas the server, they have to do more. They have to deal with lots of clients. So that's why you'll have one dedicated computer to deal with all these clients and not playing a game with one person handling the server also, because it does eat up more processing to handle all these different people playing the same game at the same time. So that's our socket. Our IP address. Okay, so what's an IP address? An IP address is basically where is this located at, right here. So for instance, 192.168.1.1 would be say the location of the server on a private network, because that's a B-class private network. I'm not going to get into that right now. It's just needless to say, that is a private network here. So say that's where our address is. So this thing's going to have an address for our server. Our clients are each have an address, so that the server knows how to communicate back to them, right? Now it's doing the addresses as green here. So each one has its own address, and then that way we can communicate back and forth to it. Cool. And then we have a read buffer and a send buffer, because we need to read and send messages back and forth. So the way we do that is we store the data into a buffer so that we can read it in. Currently I only have it to where you can read in 0.5 meg at a time, and then it updates several times per second anyways. So it's not like you're gonna get most likely someone's connection is not going to be so fast that it wouldn't be able to keep up with this. If it is a problem, you can always increase this value here for your read and send buffer, but probably in all reality 512 is more than enough to handle the data just coming back and forth to the server. But yeah, we do a buffer here, and the reason why we're going to do a read buffer and a send buffer is we want to read all the data in at once per message, right? And then we want to send all the data all at once and per message, and so that way per client with the server, and then that way it saves processing, because the more we can buffer before sending back and forth, of course, the more efficient it is. But you have to be careful with this, because if you're sitting there waiting for a long buffer, then you have slow interaction with your client because you're buffering so much. So you have to find a nice, nice balance point, if you will, for buffering and sending data. Because realize, if you're going out there and you're receiving the data on a regular basis very quickly, then you're not getting to buffer as much. It's going to slow you down because you're having to do a lot of processes before you start reading in the data again. So that's going to slow down your actual reading and sending back and forth between the different clients. But you need to have it to where it is sending out to the clients quickly enough in order to be real time in the game. Otherwise, you'll have lag. So that's where you have to find that balance point, or that optimization point, where you get the least amount of lag by having the right size buffer, if you will. Make it too big, it'll be too slow. You make it too small, it'll be too slow too. So you have to find the middle point, if you will, between the two, where it's going to be the fastest speed. And you can do that with just testing analysis of running the game and testing out the different buffer sizes in order to find out where you're going to get your best performance point. And you can make these as parameters in a GUI system, where you can sit there and set this graphically if you want, or through command line, however you want to do your server, doesn't matter. Well, technically you get a little more processing power if you don't do it graphically and you do it command line, but we're doing ours command line here for the server for now. But for ease of use for a lot of administrator type people, and well, Linux people, administrators tend to be more comfortable with the command line, but a lot of people aren't. If you're having someone for like a just regular Joe there setting up their server, then you really need to make it to where it can be easily set up and not be confusing to people. So most people are going to be comfortable with the graphical GUI interface, and so I suggest you set that up for your server too, particularly for game. You might be able to get away with that on some other ones, but for the game side stuff, you really do need a GUI for it. And with the way we've coded this application, it's going to run on Windows, Linux, Mac OS X, basically everything you can imagine, pretty much. And Unix, of course. Mac OS X is Unix anyway, it's FreeBSD Unix. Okay, so we have char, here's our send buffer. And I've kept my send and receive buffer the same. They can be different. You might find that a read buffer of a certain size is a better performance than, and a send buffer of another size is a better performance setup. You know, maybe you're receiving more than you're sending, or maybe you're sending more than you're receiving. You know what I mean? So if that's the case, you know, maybe you have a certain buffer size that gives you a better performance. So you can find this out through testing and just tweak the values in order to do performance analysis on the setup, and come up with some nice, good figures for that and make those your defaults. For me, I just did 512 by 512 here just to keep things simple. Okay, close curly brace, semicolon here. And then we're going to do static here, space SDLnet underscore socket set space socket set here. I'm going to do this for the name here, equals null here, all caps, semicolon. Null means nothing. I want it to have no value at all. Alright? And socket set lets you hold multiple sockets. Okay, so we have our socket, individual sockets here for each client, right? But this would hold all our clients plus our server socket in it. So this holds all the sockets for the entire network in one socket set. And this way we can use, what we use this for the socket sets is to see if, hey, have we gotten messages sent to us? And then we only update and we only read in for the clients where there's actually a message for us. So this way we don't waste time reading a message, waiting for a message from a client who hasn't sent us anything. We only look for messages sent by the clients, and this way it's an optimization for the server to make it run faster. So that way we don't, again, waste time looking for data that's just not even there from a client. And that just makes sense. TCP socket here, space server socket. This is the server socket. Now I just did it by itself because I didn't see a need to make a whole special structure just for the server. Instead I have the server set up as just regular variables here, and there's not as much to it, I'm afraid. It's just simple. So it's great. We just do another TCP socket here and server socket here. Now what TCP is, there's two different formats here. There's TCP and UDP. TCP is going to have a one of the 8 bits. It's going to be your check to see if you had a failure when sending. It's your parity bit, as it's called, and it's going to be a 0 or 1. So it's successful 1, 0, not successful. Whereas UDP, you do your error checking on the actual applications themselves, and so you have to check the data, make sure the data is coming through good, and that you're doing a resend for getting the data in if something doesn't come through the way it should. So with that, it's rather important that you do your sockets, your setup depending on how you're going to do it. Now we're going to do TCP in this case because we want the network set up here for the connection to be using the bit for the parity for handling it for us. So that way, if you're wanting to get a message sent from point A to point B correctly, TCP is going to be your friend. But if you want to send the message faster from point A to point B, then UDP is going to be your friend, because UDP is going to be faster because it uses that 8th bit as more data to pass through, and we don't have to do the parity checking and all that stuff on it. So instead, that's done on the application and not through the network. So in this way, you know, there's definitely times where you prefer to be UDP, and there's other times where you prefer to be TCP. As an example of, say I need to copy a data file exactly from one place to another, I probably want to do TCP for that, because I want to make sure that all those bits for that file are exact, and I'm getting the exact file. Otherwise, the program won't run and work correctly if I'm missing part of the program, right? So TCP is probably going to make a lot more sense. Whereas if I'm trying to send like maybe images from a video camera or something like that, maybe UDP makes more sense to me, because maybe I don't care if some of the pixels get dropped or whatever in between the frames. What matters to me more is that the frame rate stays up, so that I get a nice video experience and that I don't have it bogging and slowing down. People may not care if a few pixels get dropped here or there or whatever, you know what I mean? We might even be able to average and fill them in on the application side if there are pixels missing. So, you know, yeah, may not matter to you, you know. Whereas, you know, on the other circumstance, it does matter. So, totally depends on you. Now, how do we get this IP address? Now, we already went over this earlier, but let me just do it real quick here again. If I do ifconfig here in Linux, I'm going to get my IP address. And in this case, on my computer right now, I'm 192.168.11.129 in this virtual network. And that is my IPv4 internet address. I can have an IPv6 too if I'm so allocated by the router. Right now I'm not been given a address right here. Here's my MAC address, or my hardware address for my actual virtual Ethernet connection. Now, if I'm on Windows, I need to do ipconfig inside the command console or terminal, or whatever you want to call it, in Windows, DOS prompt, if you will. And that will give me a similar layout as far as information goes on Windows. So that way I know what on earth my IP address is. And that's where it came from. Okay, so client type here. I call it client temp. And the reason why I'm doing client temp, so that way when I'm adding these different sockets, I am adding in the values for my list of sockets. I'm going to do a list of sockets to have basically all the clients connected. So I need to see, I'm going to have a list of, let's put it this way, we'll have a list of clients that are connected to the server, and they're going to be stored in our list variable. We're going to go over here in just a second. I use a temporary client that I am setting up the connection with on the server as it gets communicated, and then once everything goes through correctly, then I simply just add that temporary client to the actual client list, as now it's a valid client as part of the server, and now we can start receiving messages from that client. So I'll go over this when we're starting to do it, but you'll see it makes more sense when I get to the code further down here for our client temp here. And of course it's of type here, struct client type here. Very cool. Int max num clients equals, in this case I said 16, but you could say more. Maybe you want 64 or 32 or whatever. Depends on what your server can handle as to how many you want. I would actually make this a variable where you can make this adjusted at the graphical at runtime, where you're setting up your server here, and you can add a GUI window where someone could set how many clients they want to allow to be connected to the server. Right now it's just hard coded in, but if you're doing this as for real, I would make this a variable that you could then read in for the number. Unsigned int32 here space len for finding the length, comma, and then we're also going to do the result for the result we get back. You'll see that later. Semicolon here. Bool app quit, comma net quit. This is for quitting the application, and the other one's for quitting the network connection. I think I still kept that. I'll have to double check. I may need to delete one of these variables. uint32 here space IP convert semicolon. So unsigned int32, and then we're going to have an IP conversion. And what I'm doing with this is it comes out stored into just an integer value for the IP address. And basically what I'm doing with this convert is I'm converting it out to a human readable, like 192.168.32.1 or something like that, right? That's human readable. The number as it's stored is not human readable. So we have to extract that number, and so that gets into a conversion that we'll do later. And I'll get into how that works. Unsigned int here 16 space port convert, and then we're going to do another conversion, but we're going to convert for the port to get it out. Okay. Matter of fact, I'm not sure if I ended up actually doing a port conversion, but oh well. I created a variable to do it. Alright, so anyways, client socket list. So here's how we're going to do creating our variable for our socket list here. std : list, open greater than less than signs, client type here. And it's that client type we did up in our struct, and I called it clients because this is going to be our list of clients. So this is going to hold all our clients on the server. Alright, cool. We have int space main here, open parentheses, int space argc, comma char space star star argv, close parentheses. And again, this is the number of arguments being passed into our program, and this is the list of arguments as a double pointer to the data list in memory. Alright, so open curly brace here. If open parentheses here, SDLnet underscore init, open close parentheses, space less than 0, close parentheses. Open curly brace here. So if it initializes, then it won't be less than 0, like -1 for instance. If it is, however, then we're going to output the error. So we're going to do fprintf here, open parentheses, std error, so standard error file, comma, in quotes here, SDL underscore init, colon, space, %s for string, that's what the %s is, /n here, close quotes, comma, SDLnet underscore get error, open close parentheses, semicolon here. Then exit here, open parentheses, exit underscore failure, close parentheses, semicolon. That's all caps there. Exit failure is all caps. Close curly brace. So what does that do? That kicks out that, hey, we had an error in our error file with SDL underscore init, and here is the error. And so it's going to display that error here. Awesome. So it lets us know exactly where the problem is and what the problem was as it's outputted to our standard error file if we have a problem, and then we can pull up that standard error file and see the actual failure, which is great. In Linux, however, this isn't going to get kicked out to a separate file like it will be in Windows. Instead, it's going to get kicked out to our console as we run the program. So be aware of that. It's actually going to get displayed to the screen. Terminal stuff is kind of different in Linux for programming. Resolving the host using null makes the network interface to listen to it. So alright, so we're going to resolve the host. Wow, that's a really screwed up sentence. And make the network interface listen on the port. We're going to listen on the port. And the port we're going to listen on is going to be, I just said 7770. Now, you don't have to do this. You can say anything you want, but key thing here is you do need to say a relatively high number. You need to be about above 1024 for your port, because below that is standard servers. So that is a problem if you don't set it to that. I went with this number here because it's very unlikely that another server will have this port. So I did that on purpose. Note that if someone has a firewall, they will need to open this port on their firewall. Otherwise, the server and client cannot communicate with each other. Now, we don't have to worry about this on Ubuntu Linux. This is really cool. They don't have a firewall per se. They have a built-in firewall system, if you will. Basically, when an application runs and needs a port open, the system automatically opens the port for you. Otherwise, all other ports are automatically closed. So at any point in time, the ports are automatically closed, and you don't have any ports that are just sitting open for any particular reason. And then the ports only open when there's a need for them to be open. So that's awesome. It's very straightforward. It's very easy. It makes a heck of a lot of sense, and keeps you from having to even mess with a firewall, basically. And it's beautiful. I mean, it's just a really great idea. And so that makes life a lot easier. Basically, you don't have a port open where someone can hack into your server unless there's an application connected to it. You know what I mean? In which case, the hacker's corresponding with that application. So this makes it a lot easier, or I should say cracker, because it's really more what someone breaking into a system is called a cracker. A hacker's just a loose term, because a hacker could be someone that's a good person who makes a patch to a program too, and that's also a hacker. So it doesn't necessarily have to be a bad thing. A cracker is a bad thing, though. They're a person who breaks into software or breaks into a computer network or into your computer or something like that. That'd be a cracker. So that's the difference between the two. So if SDLnet here underscore resolve host, open parentheses, and server IP, so our IP address for our server, okay, comma null, comma 7770 here, close parentheses for our port. Now we're saying null here because we're going to make this our server for resolving our host. If I didn't say null, then it wouldn't be the server. So we need to say null at this spot here, because that's what makes this our server for resolving the host. Okay? That's key here. Yep. So if there's a problem with this, fprintf here, open parentheses std error, so standard error file here, comma, in quotes here, SDLnet underscore resolve host colon %s, again that's string, /n, close quotes, comma, SDLnet underscore get error, open close parentheses, semicolon. Right, and that's going to output our, if there is a problem, if it's like -1 or something like that, first response code, then it'll automatically kick out to our standard error file. We'll append the SDLnet underscore resolve host here is where the problem is, and this is the error. And then we'll exit on exit in all caps underscore failure, close parentheses, semicolon. Alright, close curly braces, and then we're over to the next one. We're going to open a connection with the IP provided and listen on the host port. Alright, so what's the IP address provided? Well, that's going to be our server IP address. So we're going to say if here, open parentheses, exclamation mark for not, open parentheses, server socket here equals SDLnet underscore TCP underscore open. So we're going to open up a TCP connection. Alright, I'm just going to say open parentheses and server IP, close parentheses, close parentheses, close parentheses. Okay, what just happened? Alright, well, what just happened is we just passed the server's IP address into this function. Now over here, it got the server IP address from when we were resolving the host. When we resolved the host, we said, hey, did this work? You know, were we able to set up our port and our connection here? And the answer comes back with, okay, so here's our IP address, and stored into, it'll get stored. That's why we're passing it by reference here. So we're passing in the memory location to that data point, and then it's going to put that data directly into our variable, and our variable is going to get set here for server IP. Alright, and of course the return type is whether or not the function passed or failed. Over here we're also passing in our server IP address. to open up our connection. And it already knows what port to do it on because we did that over here when we did our server IP, because not just the IP address gets stored in here, but also the port. And so when we're telling it what port we'd like to open on, requesting the port what we want it opened on, that the actual port got stored over here in server IP. So that's something key to understand and to know about. Yeah, so this IP address has more than just the IP address, and it also has the port number too stored in it. And I'll get into how to access those in a bit. So basically we're passing in the IP address and the port. In this case it's the server, so it's going to be our IP address and our port that we'll be opening. So it's going to open up that port for the server, and it's going to do it on our IP address. It's going to allow us to listen for clients to connect on this address, on this socket here. So when it returns back, we get a socket here, and it's going to be our server socket that gets replied back from this, and that whole data, basically data array packet, whatever you want to call it, gets stored into our server socket variable here. All right. So if it doesn't go well, if we get if it's not a good connection, if things don't set up correctly, then we'll do a fprintf here. That's what that not's for. Open parentheses std error, comma, open quotes here, SDLnet underscore TCP underscore open colon %s/in close quotes, comma, SDLnet underscore get error open close parentheses semicolon here. And then we're going to do exit open parentheses exit underscore failure close parentheses semicolon and then close curly brace here. So now we know where it's going to fail at here. SDLnet TCP open. %s of course is for the string value, so we can see what error it's going to be. And that also gets put in our standard error file. Alright, so next.